Okay, this is the video for 2.6 rational functions. Okay, I will be able to graph rational functions. So, what is a rational function? It's just one function over another function. So if we have f of x over g of x, where or when g of x is not 0. Okay, so we're going to graph this function, and below are all the properties we're going to need to identify to graph the function. Okay, so first, the y-intercept. Well, the y-intercept is the value when x is 0. Okay, so if we have a 0 for x, and notice that I'm writing this as a point, you should too, but the y-intercept is a point. So if we have a 0 for x, plug in 0 in standard form for x and simplify it. So we're just going to take this, and we're going to plug in 0, and then we're going to simplify. And after doing this a few times, you're going to probably notice that you really just have your constants that you need to simplify, because everything with an x is going to cancel out, and so this is just negative 1/2. Y-intercept is negative 1/2. All right, so once we get through all these things, we're going to actually plot them on that graph up there, but let's get through all this first. So when in factored form, a whole is when your equation is in factored form, it cancels out. So the x that would make a 0 cancels out. So a whole is a point. So find the y value by plugging the x value into the factored reduced version. So we're just going to take our equation here, and we're going to factor it. Notice that the numerator here is a difference of squares, so I'm going to factor that as x minus 2 times x plus 2. And then the bottom I can factor as x in the front, and then I need to come up with something that's going to multiply to 8 and add to 6. So that would be 4 and 2. Okay, so what cancels out here? Well, these are the exact same, so they cancel out. So what that means is there is a whole where this x would make 0 here. So if these didn't cancel out, this would be an asymptote, because this would make 0. But in this case, since it actually does cancel out, we have a whole where x is negative 2. And then we need to find the y value. So we're going to take the y value and plug it into the factored reduced form. So we would have negative 2, and I'm just taking this, negative 2 minus 2 over negative 2 plus 4. I get negative 4 over 2, and so my y is also negative 2. And just note that's a coincidence that they are the same. That's not always going to happen. Okay, so a vertical asymptote is, like I just said, it's when the denominator is 0, but when it's not a whole. So when the denominator is 0, but not a whole. Okay, so we found the whole. So that means that we cannot have a vertical asymptote at negative 2 because it canceled out here. What we can is use the factored and reduced version, set the denominator to 0, and solve. So we can use this version right here, so x minus 2 over x plus 4, and then it's the denominator that would cause an asymptote. So if we have a 0 in the denominator, where would that occur? So I'm just going to set the denominator equal to 0, and I'm going to solve this little equation. So the asymptote would be at negative 4. Now, this is a line, so I want you to write the answer as the equation of a line. So vertical is an x equals, and it's going to be at negative 4. Okay, what else do we have on here? We can still find the y-intercept. So the y-intercept is when the y value is 0. Okay, so I'm going to set up my point here. Remember that this intercept we're going to write as a point. I'm going to set up my point with a y for 0. Now, looking at this equation, it looks like it's kind of confusing to solve this. So basically, you're trying to figure out when y would be 0. So if I just put in 0 here, I would then have to solve this whole equation. But there's a simpler way of doing this. In a rational function, this is when the numerator is 0. Let's write that down, and I will talk about why. This is when the numerator is 0. Okay, so if you look at this, and actually it says use the factored reduced version, that's because we want to already get rid of that hole. Okay, there's not going to be an x-intercept where there is a hole, so that's why we're going to use the reduced version. So x minus 2 and x plus 4. Well, when would this be 0? If we equal this to y. When would y be 0? Well, this would be 0 when the numerator is 0, because 0 divided by anything would equal. Okay, so we're going to set the numerator to x minus 2 equals 0. Solve this, and we get x equals 2. Okay, so what we found here is the x value when y is 0. Okay, so there's going to be an intercept at 2, 0. Okay, horizontal asymptote. Pretty much filled this entire box here, so there's not a whole lot of work. But you're just going to look at the leading term in standard form. We already did this in the first unit. So if the bottom is growing faster than the top, then there's a horizontal asymptote at y equals 0. If both are growing at the same rate, then there's a horizontal asymptote at y equals whatever the simplified lead term is. And so we're going to do a few of these, and if you're still kind of struggling with this, please ask questions about it. And then if the top is growing faster than the bottom, then we're talking about end behavior. Then there's not a horizontal asymptote, and we need to actually divide to find the slant asymptote. So we're going to look at a few different equations so we see each of those things. But let's just look at this one for now. We have our leading terms here, x squared over x squared. So coming down here, that's the only thing I need to look at. I need to look at x squared over x squared. And then I need to decide which of the three things is happening here. Well, is the bottom growing faster than the top? What we're looking at is the exponent to see if the bottom's growing faster than the top. And since they're the same exponent, the bottom is not growing faster than the top. Neither is the top growing faster than the bottom because it's the exact same exponent. So what's happening then is we're going to simplify this, and the lead terms are going to make our horizontal asymptote. So when there's nothing here, there's just a 1. So when I simplify this, I get 1. So my horizontal asymptote is a line, so I'm going to write this as an equation of a line. And it is y equals 1. Okay, so we have a lot of information here, and we can plot this, but we're probably going to need more points to actually find out what it looks like. So let's go ahead and plot what we have so far. We have a y-intercept at 0 and 1/2. So right there is on our graph. We have a hole at -2, -2. So not only do we know there's a hole there, but we also kind of know where our graph is, what it's going through. That kind of helps us plot it because it's just another point. Even though it's not a point, it's a hole, but it's another spot where we know where our graph is going. All right, we have a vertical asymptote at x equals -4. So we're going to come here to x equals -4. 1, 2, 3, 4. And we draw an asymptotes as dotted lines, because remember, it's just an invisible line. Then we have, let's see, what else do we have? We have a point at 2, 0. So 1, 2, 0 is a point. So I'm kind of seeing that I have a graph going like this. And then lastly, we have a horizontal asymptote at y equals 1. So we're going to draw that in as well, y equals 1. Okay, so now let's draw on our graph, or what we think we have so far. We have a few points here, and we have an asymptote, so we know that coming from here, it's going to approach this but never touch. We can follow the points that we have. It's going to approach this asymptote and never touch. And now we just need to figure out, well, where's the rest of the graph? There's nothing going to be up here, because otherwise it wouldn't be a function. So we just need to find out, well, is this over here, the graph, is it below or above this asymptote here? And so the way to do that is just to plug in some points. And it doesn't matter if you use the reduced version or the original version of your equation, because you're still going to come up with the same answers. So what I'm saying is this is -1, 2, 3, 4, 5. Let's see what's happening at -5. Let's see what's happening at -6. So I'm going to evaluate the function at -5. Again, it doesn't matter if you use the reduced or not. The reduced is usually easier to figure out because it is factored and reduced. -5 plus 4. So we have -7 and we have -1. So we get a +7 out of this one. And I'm just going to go one more step here and get another number in here just to be sure. So -6 minus 2 and -6 plus 4. And at the top we have -8 and the bottom we have -2. And this reduces to a +4. So let's plot these points here. We have the point -5, 7. And we also have the point -6, 4. So -5, 7, -6, 4. Let's see if I can remember up here. -5, 7. So 1, 2, 3, 4, 5, 6. We're off the graph here. -6, 1, 2, 3, 4. So we can kind of see this as it moves left, it's getting smaller, but we also know that because we have an asymptote here, it's going to look like this. Okay, so you only need a couple points to get the general shape here, and this is what this looks like. And then you can always, I want to be able to see your work, that you did all this to find it, but you can always confirm this on your calculator or Desmos. And that's really a good idea, to go ahead and do it and then check Desmos to see if you're right. All right, so let's look at another one here. Okay, graph the following rational functions. So let's go ahead and make a list of what we actually need to do this. We're going to need a y-intercept. We're going to want to find out if there's any holes. We're going to see if there is a VASI for vertical asymptote. We're going to see if there is a HASI, horizontal asymptote, and we're also going to find out as far as x-intercepts. Okay, so y-intercept, now remember we're just plugging in 0 to find out. So we're going to take 0 for x, plug in zeros here. Well, that pretty much gets rid of, don't cross out yours, I can erase mine. Gets rid of all of that. So we just have 4 over -2. Well, 4 over -2 is going to give me -2. Okay, next, holes. I need to factor for holes. I need a factor for a few things anyway, so let's go ahead and factor. The top can be factored. The bottom's going to stay just the same. So we have x minus 2 on the bottom, and the top is going to be x plus 2 and x plus 2. It's a perfect square trinomial, so you could have also put this as x plus 2 squared, either way. The important thing to see here, though, is that these are not going to cancel out. There's nothing that matches up here, so no holes in this graph. All right, vertical asymptote is where the denominator equals 0. So I'm going to do x minus 2 equals 0. I solve this little equation, and I have x equals 2. And a vertical asymptote is a line. It's a vertical line, and the equation is x equals 2 for that vertical line. Okay, horizontal asymptote. Now we're going to look at those leading terms here. So we have x squared over x. And we can see at the top is growing faster than the bottom. As we put in bigger numbers, this keeps getting bigger and bigger and bigger, which means that this whole function, as you plug in 10 and then 100 and then 1,000, this whole function gets bigger, which makes the y get bigger. So in this case, there is no HASI, no horizontal asymptote. What there is a slant asymptote. Slant asymptote. All right, and then to actually find the slant asymptote, and I'm going to move this down a little bit. I'm going to need some space here to do some dividing. To find the slant asymptote, this just simplified to x here. So just another observation here. If this simplifies to x, as we put in bigger and bigger numbers, y is also going to get bigger. Okay, so we're going to do some dividing here. I could do synthetic division because this is in the form of x minus something, or yeah, I just have a binomial here. But I just want to look at long division one more time in case that we do encounter a problem where we do have to do long division, like if there was a squared on the first term. So I put my divisor out there. I'm going to put what I'm dividing into in here. All right, x goes into x squared x number of times. So x times x is x squared, then negative 2x. Now remember, you're going to subtract this whole thing, so that means negative and positive. It's going to change the sign on both of them. These cancel out, and I now have 6x. Bring down my positive 4. X goes into 6x 6 times. And then I multiply and I get 6x minus 2. Subtract, and I get 6 down here. And this is going to be my remainder. And actually, when we're looking for the slant asymptote, we don't care about the remainder. So our slant asymptote is just this part right here. So y equals x plus 6. This is a line in slope-intercept form, so we're going to graph that in a little bit. Okay, we still need our x-intercepts here, and I already wrote it down, but we're just looking for where y is 0. And keep in mind, y is going to be 0 whenever the numerator is 0. So the numerator is going to be 0 when we have a negative 2 here. So I came up with negative 2, 0 for my x-intercept. All right, I have all the parts except for maybe some additional points, but let's see what we have and see where we need those points to be. So we have 0, negative 2. We also have a vertical asymptote at x equals 2. So we'll go to x equals 2 and draw in a dashed line. And then we have an x-intercept at negative 2, 0. We have a slant asymptote at x equals 6. So we're going to go up to 6. 1, 2, 3, 4, 5, 6. And then our slope is 1 over 1. So you do need to remember how to graph a line to do this. Just kind of drawing it in here. And there's our slant asymptote. Okay, did I put everything in there? I believe so. So right now, the only thing we have here are these 2 points. And because we know it's not going to cross those asymptotes, we can draw that in. But then what's going on for the rest of this? Okay, I can see up here nothing's happening, but is the rest of my function graph up here, or is it here? So now I'm going to add in some points and see what happens. So 1, 2, 3, 4. I'm going to put in 4 into this equation here. So some additional points I'm going to evaluate at 4. So I have 4 squared. I have 4 times 4. A lot of 4s in this one. Plus 4 all over 4 minus 2. Let's figure out what this is. Okay, I calculated this out and I do get 18. So 18 is somewhere way up here. So just to give us an idea, I'm just going to draw it like this. Okay, so you can see that we want to be exact with all our parts here, but then when we're sketching these in, don't worry about finding a million points to make sure you're finding exactly where this is. I just want you to be able to find the location and show me that it's not crossing the asymptotes and actually passing through the holes. But I'm going to be looking for all this work to make sure you know how to do all this and find these parts. Okay, last one we're going to do together, and then I'm leaving one for you to do, but I just want to do this one so that we can talk about these parts here. So let's try to power through this because I know this video is getting kind of long. So y-intercept, I need hole, I need vertical asymptote, I need x-intercept, I need horizontal asymptote, and then I will need some points. I can see right here that my horizontal asymptote is not going to be a slant asymptote, so I'm just going to go ahead and write points right here because I'm not going to need extra room above. Okay, so my y-intercept, feel free to do this one on your own, to pause the video and give this a try and then rejoin me. That's always a good way to learn. Okay, my y-intercept is going to be where x equals 0. My y is negative 4/3, so that I can plot this, I'm going to do negative 1 and 1/3. My hole, well, let's go ahead and factor this out. I have 2x minus 2 all over x plus 3. No holes. My vertical asymptote is a line at x equals negative 3, so where the denominator is 0. My x-intercept is going to be where the numerator would be 0, so that would be at 2. So 2, 0. My horizontal asymptote, well, now I'm looking at these front 2 terms, so I have 2x over x. When I simplify this, this would be 2, so that means my horizontal asymptote is at y equals 2. And then let's graph these before I decide if I need points and where they would be. So 0, 1 1/3 is right about there. No holes. My vertical asymptote is at -3, 1, 2, 3. Wait, 1, 2, 3. Just like this. My x-intercept is at 2, 0, 1, 2. Here's my 0. My horizontal asymptote is at y equals 2, so coming up here. There we go. And because I have these 2 points here, I know it's going to go zoop, just like this. And now I just need to find, okay, well, is it down here or is it up here? I'm going to plug in a -4 into my equation and see what happens. So I'm going to evaluate at -4. And I have 2 times -4 minus 4 all over -4 plus 3 equals 12. And if I want to do another one just to be sure, do -5. We have 2 times -5 all over -4. Because you could make an error in your calculation, so it's nice to do a couple points and make sure it makes sense. Get -7. Okay, so -4 and 12, -4, 1, 2, 3, 4, and 12 is someplace way up there, but let's see if this makes sense with the other point that I came up with. So -5, -5, and -7. So it does look like as I move this way, it is coming down, right? So I think if I do some points over here, I'm going to see a trend that is coming down like this. So feel free to do that. Feel free to plot as many points as you need to feel confident that you know what's going on here, but I'm feeling confident it is going to look like that. All right, so I just want to talk one more time about limits, and then talk about left limits and right side limits. All right, so the limit as x approaches -infinity, f of x is doing what? So it says, what this is saying is x goes to the left, okay? As the x's approach -infinity, what are the y's approaching? Well, the y's are going to come down here and get closer and closer and closer to 2, because they're not going to go over that horizontal asymptote. The limit as x approaches positive infinity, or as x goes to the right, we're also approaching 2. It's coming up, but it's still approaching 2. Okay, what about the limit as x approaches -3 from the left-hand side? Right, so x gets close to the left side of -3. So here's my -3 asymptote, and I'm getting closer and closer from the left-hand side. What's happening to the y's? Well, the y's are growing as they get closer. The y's keep going up, up, up. So the y's are approaching infinity. And then as I approach -3 from the right side, or the positive side, right, this is the positive side, as I'm approaching -3 from the right side, my y's are getting smaller, smaller, smaller. So that means it's approaching -infinity. All right, that's the whole thing. Give this a try, guys. You have plenty of steps in here, plenty of notes to look back on, and give this a try. And the worst that can happen is that you're wrong. So do it in pencil. All right, thanks for watching.